graphs of basic function relations and symmetry. So first we're going to talk about continuity. Basic continuity means if I could draw it without picking your pencil, it's continuous. So like look at this picture here. That's continuous everywhere. Now this graph, I'm drawing it, I got to stop at that hole and then go on again. So it's continuous everywhere except for 3. This one, right, drawing it, continuous until -2. I can't go from here to here without picking up my pencil. So it's discontinuous at -2. So that's what happens here. So it's continuous, stops at 2, and continues again. Continuous, stops at 2, continues again. So it's probably easier to tell when something is discontinuous. It's when you have little holes or vertical asymptotes or a jump here. That's when it's not continuous. So this problem wants to indicate the intervals of the domain over which the graphs are continuous. So on the first one here, well, it's from -infinity to positive infinity. So -infinity to positive infinity. On this one, it's from -infinity to 3. I have to stop at 3. Like 3 is the problem here. So it's going to go from -infinity to 3, and then I could go from 3 to infinity. Right, so the stop here is at 3. So here to here. On this one, -2 is a problem. So I could go from -infinity to -2. Anytime you put two like intervals together, we use a little union symbol, and we go from -2 to infinity. So that's where it's continuous. It's not continuous here at 3, it's not continuous here at -2, but everywhere else. I guess another way to write that is just saying where x does not equal 3, and where x does not equal -2. So that's probably an easier way of saying it. Increasing, decreasing, and constant functions. So when we read graphs, we read them from left to right, like reading a book in America. So you want to go from left to right. So when it's going up, we call that increasing. When the slope is positive, it's called increasing. When it's going down, it's decreasing. When it's being straight, it's constant. So rising, increasing, falling, decreasing, straight, constant. Now when I ask you to tell me when is it increasing or decreasing, I'm looking for the x values here. So it's like when. So x values. All we care about are the x values. So when is it increasing, when is it decreasing? So that's a very key point. X values. So for example here, find out where it's increasing. So A. So look at, we're going from left to right. It's decreasing, increasing, then constant. So it's increasing from here to here. So from 1 to 3. So we'll say from 1 to 3. And we use parentheses because like they share those points 1 and 3. So with parentheses from 1 and 3, that's when I'm increasing. So again, just the x values. B, when's it decreasing? Well, it's decreasing from here all the way to here. That's an arrow. So arrows are always parentheses, -infinity. And then we're going to stop at 1. Right, so from -infinity arrow all the way to 1. Again, when. I don't care about the y at all. It's all about the x's. When is it doing it? C, was it constant? Well, it starts right here at 3, and then all the way to the end. So 3 to infinity. What's my worst infinity yet? That one might be even worse. Okay, so we got that. What's the domain and range? Domain and range is just the whole graph. So if I was doing domain and range, my domain here would be -infinity. You got to stop where it's discontinuous at. So you got to stop at 1. So it goes from -infinity to 1. My domain. Then it starts up again, and I go from 1 to infinity. Right, so it goes all the way to here, then it stops for a second, then it starts again. My range, lowest I see is -2, high, and then it goes on forever. So -2 to infinity. Sorry, +2 to infinity. Right, so that's the lowest. My range is low to high. So lowest I see right there is at 2, then it goes all the way up. And they overlap here, but that doesn't matter. It's just like, is there ever a break? There isn't. So from 2 on. So that's that one. The one right here. So we're going to do A. Where is it increasing? So let's look at it from left to right. So it's decreasing, constant, increasing. So again, only the x value I care about. So when is it when? So 4. So it's 4 to infinity. Right. So from 4 to infinity. And then where is it decreasing? So it's decreasing from here to here. So from -infinity to -1. C, where is it constant? It's constant from here to here. So from -1, again, x values, -1 to 4. Only care about the x values, -1 to 4. Unless we're doing domain. Unless we're doing range, So there we go. Again, always parentheses with those. Once you get to minimum range, then you can add in the brackets, but intervals are always parentheses. Interval of increase and decrease and constant always parentheses. Domain looks like it's going from negative infinity all the way to infinity. So all row numbers you can also write if you want to do that. E, the range, the lowest I see is 3, and then it goes all the way up to infinity. So bracket 3 to infinity. Again, bracket because it actually takes the value of 3. So that's how you do increasing, decreasing, and constant. So we're going to talk about some basic functions we should all know. So constant function is one where your function just equals a constant, like a number like 2 or 3. So like here, they all equal 5. In that case, the graph is always constant, it's never increasing or decreasing, and it's continuous, right? The whole way, it's continuous. This is called an identity function, just where the f of x equals x. So think about it like a slope of 1, but with no y-intercept. So you start at 0 and then go up 1 over 1. That's called identity function. In that case, it's always increasing throughout the whole domain, and it's also continuous everywhere. The squaring function is symmetry with respect to the y-axis. So when something's symmetric with respect to the y-axis, that means like, so remember this is x and this is y. That means you could flip it across the y-axis. You could fold it like a book, is what people tend to think. Book on the y-axis. Right, so I could fold it in half. So if I see that here, if I could fold it in half, that's symmetric across the y-axis. The way you could show it mathematically is by plugging in negative x and see if you get f of x back. We'll do that in a second. So it sounds funkier than it is. It's not that bad. Probably the most famous example of a graph that's symmetric across the y-axis is the quadratic graph, x squared. So look here, right? If you fold it in half like a book, the two sides will match, just like that side. So that's symmetric across the y-axis. And if you plug it in, this is the thing I talked about, right? If we want to plug f of negative x in, what does that mean? Well, we'll plug it into something squared to be negative x squared. And when you square a negative, the negative goes away. So you see that. So it shows that it's symmetric across the y-axis. So that's like the mathematical way of doing it. This graph here, it's decreasing and then it's increasing, so it switches, but it is continuous throughout the whole graph. The cubing function is symmetric with respect to the origin. Symmetric with respect to the origin is kind of funky. So here's the origin. So if you can see, we're going from left to right, like we're going kind of curving up, and then when you're symmetric across it, so you start repeating yourself. So now you start curving that way. So it's kind of like you can kind of think of twisting it 180 degrees that way. So that's symmetric with respect to the origin. A good example of that is a cubic graph, x cubed. You can see here, right? It goes up like this, and then turns into the same thing. This graph, it's always increasing. Now it depends on the graph, but just the cubic graph is always increasing. And it continues throughout the whole domain. Now, how do you show this mathematically? How do you show that something is symmetric across origin? Well, this is how when you plug in negative x, you should get the negative version of it. So if you think about f of x looking like x cubed, if I plug in a negative x, so it becomes here. When you cube a negative, nothing happens. It just stays negative. So you get this. So this is a negative version of that. That means it's symmetric across the origin. Symmetric with respect to the x-axis. So that means you're going to fold in half, but across the x-axis now, right? So it's a book thing, but now across the x-axis. So that's just symmetric across the x-axis. Mathematically, I'd say right now we're not going to do it in this class, but we do the same concept, but instead of plugging in negative x, you plug in negative y. So those are three symmetries. You can be symmetric across the y-axis, so you fold in half like a book, like an actual book. You can be symmetric across the origin, so it kind of spins across there. Or you can be symmetric across the x-axis, so it folds in half like a laying down book. Okay. So using visual observation, determine whether each of these graphs is symmetric with respect to the x-axis, the y-axis, or origin. So look at this one, right? How could you fold it in half? I could fold it in half across here. So across the x-axis. So I guess A. This one's, you know, see how it kind of copies itself? This one's respect to the origin. Now this one, you could fold in half, x and y. So it's respect to the y. You can also fold it half this way. And it's actually symmetric across the origin too. This one's all of them. It's A, B, and C. I'll just put that into, see, these are right then, one of each. Now it's because it's a perfect circle. Let's make circles nice. If it was like an oval, it would be different. You have to like see which one it is. Okay, let's talk about even odd functions. These are actually very related symmetrize the x and y function. Actually, that's what they are. So an even function is a function that you can fold that's symmetric with respect to the y-axis. So you can fold it in half like a book. An odd function is the one that's symmetric across the origin. So that's considered an odd function. And if it's none of those two, then we call that neither. So again, even, fold in half like a book. Odd function with respect to the origin. Now, how do you show mathematically? The thing we did earlier. It's even if when you plug in a negative x, you just get the normal function back. It's odd when you plug in a negative x, you get the negative version of your function. Again, we'll talk about that more, how it's a negative version of your function. If you get some mixture, then it's neither. So using visual observation to remember whether the graph of the function is even, odd, or neither. So you want this one right here, you can't fold in half like a book, so it's not even. It's not odd because if it was down here, it would probably be odd, but it's not odd because it's up there. It has to be across the origin. So you can't fold in half like this, so it's not even, and you can't spin it across there, so it's not odd. So this is a neither. EI. This one, you can't fold in half like a book, but it actually does spin across the origin, right? So it does this thing, and then it kind of repeats itself going that way. So this is odd. I like this one. Complete the right half of the graph given the following condition. So I want to make this an odd function. So if I was to make this an odd function, right? So whatever it does here, I got to kind of repeat it by doing it down here. So it's kind of like this. So let me do that in purple. So it can look like this. So that makes it odd. So there's that one. But I want to delete it. So let me just write another one real quick. Won't be as nice, but same concept. Oops, I have to go to the origin, right? Okay, something like that. Now let's do this one in red. And now if it's even, I should be able to fold in half like a book. So whatever's on this side should match on this side. So it's kind of like this. Not my best drawing, but something to that effect. Right, so you fold in half like a book right there. Next one. Complete the table assuming that g is an odd function. So if g is an odd function, it should spin across the origin here. So most likely that's going to be 0. Now, it goes from -2 to -5. Remember, so when you're doing odd, it's not the same. It's not like you're folding a book. It flips, so this will become +5. -1 become +1, and positive 10 become -13. Right? So if it was an even function, then you just match the two sides. You just make them exactly the same. If it's an odd function, they kind of have to flip. Each function is either even or odd. Evaluate f of -x to determine which situation applies. So that's the thing, how we tell if it's even or odd function. We're going to plug in f of -x into this function here and see what we get. So it's the first one. So f of -x, remember whatever goes into here goes into here. So it's something like this, 1/2 to the -x. Now we just got to simplify it. So that's 1/-2x. And this is a negative version of that, right? So like this is the exact same thing as that, but just a negative on the outside. So this is negative f of x. Right? If you just look at this guy right here. Let me do this again. If you just look at this right here, that is what that is. So this is a negative version of that. So you get negative f of x, which makes this an odd function. Let's look at the next one. It's the same idea. We're going to plug in negative x. So I get negative x squared plus 3 over the absolute value of negative x. Right, I'm just, wherever I see the x, I plug in negative x. That's the whole point of this. Negative x squared is just x squared. Absolute value of anything is positive, such as x. So look what happens when you get x squared plus 3 over x. And that is the exact same thing we start off with. Well, I could write that as the absolute value of x, but exact same thing to start off with. So this is just f of x. So when that equals the normal itself, that's an even function. So that's how you tell if it's even or odd by doing mathematics. All you do is plug in the negative, you plug in negative x. If you get something that's exactly the opposite, it's an odd function. If you get something that's exactly the same as the original, then it's an even function. You get some mixture, it's neither. That's the lesson.